Hi, good morning. I'm Vishnu and I'm hereby presenting my dissertation. My dissertation is a fast and advanced facial recognition solution using MediaPipe neural network. So we all know about the facial recognition solutions that is available online and also in most of our products including Apple. So here the facial recognition has become more relevant because of like it provides the most sophisticated authentication as well as authorization and surveillance. Recently we have seen so many movies also regarding facial recognition happens on the real world scenarios, but actually is it happening? The AI is so advanced right now and the world is developing more secure efficient way, but it's not in a commercial way. So the most recent commercial way is what Apple did with Face ID, but when it comes to applications that is being based on cloud and like mobile applications and door cameras, still the possibility of facial recognition has to be researched. That's what we are doing in this particular research. This research focuses on using MediaPipe. MediaPipe is a framework that was developed by Google to create a fastest product. That means the most recent facial recognition applications are basically slower, and we need to find a faster one. And for better like authentication and offender recognition, that is one of the government's possibility, and attendance monitoring, like whenever a person enters a particular building the attendance can be monitored, and access control as I have said earlier. So this particular product is built on a service oriented architecture, means almost all the code base is separated into modules, which each module does its own work. So that can be used in cloud based, so like microservices and those kind of applications, or single sign on kind of applications in future. So the main objective, as I have said earlier, is to develop a product for facial recognition using MediaPipe in a low latency efficient way. That means recently the devices are becoming more and more sophisticated. So let's say a doorbell like the Ring by Amazon has like a camera attached to it, but actually did it recognized face? No. So we are thinking about like incorporating such a powerful AI tool into small devices. So for that the framework should be working in a low latency, like utilizing less resources and utilizing less energy, as well as having more accuracy. So our research objectives are to understand the concepts of AI, media pipe, face recognition, and design strategies that I have explained in my dissertation, uh, and to design a service-oriented architecture for facial recognition. And we do the comparison, benchmarking, and database handling, as well as result handling of the system. So the person should know that this is the result that we need to be seen, like kind of whose face has been shown in the screen. um, so we are using PyQt6 as the UI and to configure and customize MediaPipe framework for efficient face recognition. We are also comparing MediaPipe framework with deep face and face recognition libraries in terms of performance and accuracy. So why we are choosing MediaPipe can be justified using uh, comparison with other frameworks, other commercially available and most commonly used frameworks. So if by compare, not only by comparing but also taking the benchmark, we can understand uh, and evaluate about the possibility of creating a smaller form of devices using Jetson Nano, Sony IMX477 kind of cameras for a future industrial purpose, and to successfully implement this for further research and development, as I have said right now. So I have done an extensive literature review regarding this. So the literature basically starts from 1888, because how the face recognition is actually done is based on the facial features, that is based on like the points like eyes, nose, the position of nose, mouth, and the facial points all over the faces. So the modern day concept of facial recognition started by Francis Galton, who explained about the points, even though he used it for racial profiling. We are, for a betterment of society, we are using it for actual facial recognition and identity verification for authentication purposes. Facial recognition can be said as a subset of biometrics used in a variety of domains, from personal security to large-scale public safety, due to its identification and verification of individuals without direct interacting with the devices. 2020 and 21 saw a major outbreak of COVID-19. So the verification, like fingerprint sensors in office premises, um, cause would cause spreading of the virus. So a facial recognition system on such scenarios could actually can be used instead of um, like fingerprint sensors, or like other biometric uh, that act like touching points. MediaPipe is a combination of two deep neural networks developed by Google, built on C++, that can be accessed by Python using Packet API. That is an API that was developed by Google, and it is built on a direct graph architecture. Uses TensorFlow. TensorFlow and TensorFlow Lights are two major machine learning libraries built on an open source network. So we can actually download the TensorFlow from TensorFlow's website, and that is actually based on a graph architecture model. um, so in 2019, Lucaresi has actually done an extensive research on the topic. So we are after taking the MediaPipe, we create a face mesh that we will be discussing in the methodology section later, and that face mesh is sent to a SVM, that is support vector model, to find cause and similarity using sklearn's machine learning model. So sklearn is scikit model, that is scikit-learn model. Actually, it have a variety of frameworks attached to it, but we are using cause and similarity, and we will be using linear regression model to correct the facial position and to resize the facial landmarks. So cause and similarity is measurement of angles between two non-empty same size vectors. So two non-empty same size vectors means it is a matrix, that is basically a numpy array. We can also say as a numpy array, that is a matrix that both the matrices are not having any values of 0 or not empty, as well as should be identical. That means the like horizontal number and the vertical number of both the matrices should be matching. Like for example, 2 by 2, if we take a 2 by 2 matrix on one side, the other one that need to be compared should be also 2 by 2 matrix. So this value is so crucial while determining how similar facial landmarks of two images are. It is actually determined between 0 to 1. Mostly 1 means both the arrays are like identical. That means both the arrays have same values, and 0 means both have very distant values. Maybe from the first if the first vector has 0 0 0 0 and second vector has 1 1 1 1 1, that means it is entirely different. So thus the angular difference is calculated, and if 0 means it is not at all similar, 1 means it is similar, means identical. So this is what I was talking about, like our methodology. The application is developed on a framework that first the camera captures the frame, then the frame is the camera uses CV2 or OpenCV to capture the frame and convert it to like an image frame, and that image frame is served to MediaPipe to analyze and detect the face. And if the face is detected, it will create a facial landmark. And let's say that if the face is little bit like having a slanting position or is distorted, the facial landmarks will be actually corrected using sklearn's linear regression model, as well as affine transformation to make it centered and correct the pitch roll, and yeah, that is the spatial orientation of the image, and centering the image, if the nose is little bit to the right, it will be centered to 0. That means the image is correct. So after correcting the facial landmarks, it is converted into a numpy array, and that numpy array is compared using cosine similarity with the facial landmarks saved inside the database. So it depends upon which button the person, like the user, presses. If he presses the record button, then this numpy array will be saved to the MongoDB collection here. Or if he presses a recognize button, the data that was already saved on MongoDB collection will be collected and will be compared with the currently detected or currently transformed numpy array. And with the comparison using constant similarity, more it shifts towards 1. That means more similar the faces are, thus the person is identified. Here you can see the identified facial info is sent back to the UI, and that UI will have a video stream that actually provides a box towards the face, which says which displays the saved name on the database. So I will explain the code here. The entry point of this code is from main.py. So main.py have two threads. One is the camera thread and the other one is application. So the application is based on the UI that builds a PyQt6 UI, and this PyQt6 UI have layouts where all the buttons, sliders, and recognize button. Yeah, I have already told you the recognize button and validation button. Validation button in benchmark. So, like the camera's feedback, everything is designed. So it also have a thread, that is two threads are running. One is PyQt6 and another one is the camera thread that is done using CV2 or OpenCV. So this is one module, as I have said, service oriented. This is one service that is running, and the second service is the camera thread. We are using SVM, that is support vector model thread over here, which actually imports MediaPipe, and this MediaPipe is called here. I can show you when we run the application, the OpenCV will capture the camera frames and convert MediaPipe will turn it into media face mesh. And if the face mesh finds out there are faces inside that, like we have reduced it to detect only one face in a frame, but still if it detects one face, then what happens is the frame is read, and that frame is fed to that CV2 frame CV2, that is OpenCV framework, and OpenCV will do some flipping as well as color corrections, and after that it is fed to the face mesh process, and this face mesh will have results, that is the facial landmarks, and that facial landmarks is then the facial landmarks is sent to process faces, uh, that's a function we have written to process the facial landmarks to generate the image, like generate the landmarks and array. So it will be sent to process faces function. Here the process faces function is, so if there are landmarks inside the results, the facial landmarks are calculated and face locations are saved into an array. That array is sent to calculate pitch, yeah, and roll, like what the pitch, yeah, and roll of the current facial landmarks is. We use this function to calculate that. This function is written here using a like NP array, and from that we find out the axis, and to linearize this we uses like rotation, that is spatial rotation from sklearns, spatial transform rotation. So this rotation is happening here, like the image is skewed, or the pitch, yeah, and roll is corrected. And after correcting the facial like pitch, yeah, and roll, we will be using this to actually resize the image. We are resizing this image after estimating how much we have to resize using affine transformation, and we will be applying the affine transformation using linear regression model. So for that we have written an estimate affine transformation, and here using linear regression we are identifying how much needs to be transferred like transformed. And this apply transformation, you can see like the rotation is applied as well as the uh, like the rotation is also applied, and the linear regression, like the phase is corrected here. So after that, if the input is for recognition, we will run the recognize face function. If it is for recording, we will run the record face function. So I will go with the record face function so that it will be in a linear model. So what happens in the record phase is, like we have the embedding here. So we save that embedding into collection of faces that is being written in MongoDB. So it is hosted on a Docker environment in this computer. So these are the phases that already being saved here. So this is the array, that is numpy array, that was created and saved in the name of in the like element document as phase, and as a key of phase and value as that array. And here you can see the name is saved as a string. We are not in a production model, we are researching that, so we haven't used any IDO meta tags or any relations here, just the name is saved here. So after that, if the we will be comparing it with the when the recognition function is running. So here we run the recognize function. So face embedding is provided, like from the like MediaPipe facial landmarks after affine transformation and linear regression and spatial transforms. And the face locations are also sent just to make sure that we draw the box and display the name on that particular image. So max similarity is set as -1. That is like first value was set to the least. Then we will be slowly increasing the distances. So here we calculate the cosine similarity as the distance using like comparing with the non-face embedding and face embedding that is being sent. So here we have used a loop because we have like thousands of faces that is being saved in the database, and we are comparing each data saved in the database with the existing facial embedding, and we are saving that into like into max similarity and distance. If the distance is greater than max similarity, what happens is we save the max similarity as the distance, what the current distance is, and also we take the name of non-phase from the like the unzipped or from the for loop. So the more the similarities, the more confident the same phase, like the identity of the phase. So if we have also said a threshold, that threshold is 0.99, that means anything lower than 0.99, that means because of cosine similarity in facial landmarks of MediaPipe, the similarity would be around like uh, more than 0.9998. So we are not actually making it to 100, like 100 or something. We are taking it like if it is less than 0.99, then we put it as unknown. So when running this program, you can see how the value was calculated. So we also take the pixel landmarks that in the face, and we convert the facial landmarks to like a box inside the CV2 image. You can see here we are drawing a rectangle inside the image with a particular color combination, and we are saying like we are placing the name on that image. So this is the code base of the actual product, and we have a different benchmarking code, that is this is the different benchmarking UI, and each framework was compared with each other. I'll be discussing about that after a while. And this is the whole architecture that was designed according to TOGAF architecture framework guidelines to have the quality of the designing. And here we can see like the UI is a service that is PyQt based on PyQt6, and application code base is another service that is based on OpenCV and MediaPipe, where OpenCV is the camera controller and MediaPipe is the recognition landmark conversion library algorithm that we use, and the cosine similarity is calculated here. So the uh, flow will be like if the record button is clicked, the camera will be activated, record or recognize function, and camera will be activated based on OpenCV. And what happens is the OpenCV will access the frame that is from the camera and send to MediaPipe framework, and MediaPipe framework will generate the facial landmarks, and this facial landmarks uh, will be sent to like recording if the person wants to record, or if it is recognition, it will be sent to the recognition function like I had said earlier. So if it is recording, then the uh, sorry then the array that is generated will be saved to the faces collection. If it is recognition, then this facial landmark will be compared with the saved facial landmarks using cosine similarity, and we generate a recognition response, and that recognition response is sent back to OpenCV to generate the rectangle around the face, and will be sent back to camera stream feedback. So this architecture was created using Archimate, a software that is being used to generate the architecture, and we have created the application layer that you have seen here or like earlier, and this is the benchmarking view that I told you like we'll be discussing. Here the researcher will be using the same PyQt6 UI, but the benchmarking system has another drop down that says choose framework, and if the researcher chooses one of the frameworks like MediaPipe or DeepFace or face recognition, it will be accessing the facial images that is saved inside a folder, and depending upon recording or recognition button who he chooses. If it is recording, the train folder inside this will be accessed. Here we have train and validation folders. So we have splitted the training folder into 5 subfolders. Each the name of the subfolder says about the persons, that is the identification, and the images is used to train create the facial recognition landmarks that is being saved on the database. And this is compared while benchmarking for validation. This is compared with the validation folder. This folder names are not taken into account. This is basically to identify which person was like compared, and based on true positive, false positive, true negative and false negative kind of four-way framework, four-way feedback, we assess how much accurate the recognition system is. So we also have like after this the recognition or recording feature is checked, and the response is sent back to the PyQt UI. So we have the business layer of the product here. So it is what is happening inside the face recognition system as the package. So user presses the recognize button, then the camera is activated, then it goes to application code base, which I explained earlier, then it goes to an API interface, and which is between MongoDB database and application framework. And after application find recognize the face, it is fed back to camera stream feedback. So data flow is like from the user towards the camera to the media pipe, then to the facial landmarks, and saved or compared and sent back to the recognition response data is created, which is accessed by camera stream feedback. We are using a MacBook Pro, which is similar to a Jetson Nano because of its R64 chipset. So this is used as a small device, like instead of using a big large kind of machine learning server, we are using a small laptop to do all the work, and we create a Python virtual environment to emulate the environment this application runs on, and Docker is used to host the MongoDB server. Here this is the Docker, and MongoDB server is running inside this, and camera is another device that is being part of MacBook Pro. So this is the enlarged version of the same PPT we are discussing, and here are the research outcomes. This is the realized software in action that I will be showing you later. So the research outcomes were it is 89.92 lesser resource utilization by MediaPipe compared to deepface, and it have 8% higher accuracy compared to face recognition, and MediaPipe is 85.56% faster compared to deepface. So it is it uses lesser resources, it have higher accuracy but comparatively lower than deepface, but while taking the performance into account, MediaPipe is much more better, and also it is much faster than deepface. So as a conclusion, I have gone through the literature review that that was required to architect and benchmark this product, and during development we used TOGAF's architecture framework, that is enterprise architecture framework, to build the software architecture, and PMI based guidelines including stakeholder management. The stakeholders are university and supervisor, and the researcher itself, and like the process flow, like project development life cycle was followed on, and communication management was followed on, and the product was successfully created that I will be showing you, which can be used in real world applications. And benchmarking was also done, where the data and graphs were generated, and research show that it is possible to use MediaPipe on a real world scenario, like in a common day to day use. So let's try the application out. um, so to run the application, here we have main.py. This is the product we are having. I'll run it. Here you can see the whole application is using the PyQt6 UI, and here we have 4 buttons, and this is the percentage of confidence setting. If we press the record face button, the face will be recorded, and that recorded face will be saved to um, like MongoDB database as like face array. And you can see we have 1053 frames now available. So I will record my face right now. So it is asking my name. So you can see my face is being recorded. So when I press stop camera, the face was recorded. We can see the data increased is from 1204. So now what we will do is, we try to recognize the face. We can either use chart camera or recognize face buttons over here. You can see how faster it is to recognize the face even from the first moment. Even when I shift to side, oh, there is a threshold of 0.99. It's like here you can see if it is lesser than 0.99, when I shift for a particular angle, it will change the value. So if I show some other face, like maybe my friend's face over in my mobile, okay, this is my parents face. So it is saying like unknown here. You can see, I think it is recognizing my face again. So I will stop the camera. So it says unknown. So sometimes it have a like false positives, but we can change the threshold to more to actually identify the face. So you can see it is much faster compared to other things, and if I change it to more than a threshold, it says unknown, because that face, that location wasn't saved in the database or cannot be compared. So regarding benchmarking, we have like these folders. I have already shown the train folder and validation folder here, and I will be running the benchmark code. This is the entry point, and here you can see I have imported the benchmark from UI. So that is from benchmark. I have like imported this class, and this class have like buttons that is required to run this, and also we are creating a feedback function like 4 buttons: true positive, false positive, true negative, and false negative. So we'll be running the benchmarking. I will run the deep phase benchmarking, so I have to select the folder first. I'm just validating because all the phases are already recorded, so I will say like so. Sorry, the database doesn't have any value, that's why it's not showing. I have to change the environmental variable to benchmarking first. So you can see it was said as Ben Affleck, and the folder is Ben Affleck. So this is true positive. This is also Ben Affleck. It's a true positive. So it's Madonna. Yep, that's from Madonna's. So we can actually choose which of these buttons like is actually taking into feedback, and that data is used to calculate how much accurate a framework is. So I will just skip. So it's Monday calling. Yes, this is Jerry Seinfeld. Jerry Seinfeld. So this is how benchmarking was done, and during that time we recorded the activity monitor and how much memory it was using, how much CPU it was using. You can see the CPU usage was little bit higher over here. That was during the recording session and running session. If it is running on a instead of waiting for the feedback, killing the processes and saving the memory, if you run it continuously, the CPU load is little bit higher. So based on all this data, we created a data sheet. This is all the benchmarking accuracy sheet we have. We have actually checked 50 photos, like 5 photos, 5 images in each folder, that is 25 images. We checked it twice and found out like among these 50 images, MediaPipe detected 30 images, while among the 50 the facial recognition's dlib library picked only 14. So it is double the amount of actual face recognition libraries detect the face, and that landmarks are fed to deep face, and deep face have the highest accuracy, but the like here you can see the execution time is much higher, and the recording time is also much higher. So this is this is the median and this is the average, and for each iteration we have calculated the time required for each one. So this is the sum, and this is execution time. These are all in milliseconds, and the resource utilization is like this. The RAM was calculated initially and during the operation, and how much difference usage is. And likewise we also calculated the CPU usage during execution, and we calculated the actual usage and drawn a graph based on that. So from that information we received this research outcomes, and we are having like as I said earlier, 90% uses less resource. So in conclusion, we have successfully created the product and can be used in real life industrial applications using this service oriented architecture, and thus we can actually make the world a better place using this resource. Thank you.